Okay, so today we're going to continue going over neural nets because last time we kind of left off like halfway. So quick recap. So neural nets, modeled after neurons in the brain. It's like an artificial neural network. You have your input layer first, and it contains input neurons. So every layer has neurons in it, right? So and you also have your hidden layer, which processes and does all the calculations on that stuff. And this is where like really everything is happening, right? The hidden layer, that's where you're trying to it's where the magic happens. But yeah, you have more than one hidden layers for more complexity, and your output layer has output neurons. Obviously, he just spits out the output, right? So synapses are the pathways between neurons, similar to how synapses between your brain cells. Yay, okay. So neurons, yeah, like I said earlier with the hidden layers, hidden neurons, they're like functions. Take an output from the previous layer and it returns a value. So the inputs are weighted differently at each neuron. And I don't know what this last one says because a little black bar won't go away. Can I move this? Oh, okay.
Are you in presentation?
Mm-hmm. Doesn't it go away after a little bit?
It should.
Yeah, it should. Hello? Okay.
Wait, go to the bottom
Oh,
and
there we go.
oh wait, okay, there you go.
I'm just a late bloomer, I guess. I don't know. So
Okay.
nodes in the same layer don't get connected. Actually, I think there's one type where you do connect in the same layer, but for the most part, you don't connect between layers. No, you connect from layer to layer. You don't connect the nodes in the same layer. So you see how like the hidden nodes, they aren't connected to each other like vertically. Okay. Oh, it's back. Okay, anyways. So yeah, I think I'm just gonna go through all the recap, and then Joaquin, you're gonna go through like the Softmax and the actual like stuff. Sound good?
Yeah, sure.
I'm just gonna keep going. So, but if you want to say anything, feel free to like cut in. So types of neural networks, we have our artificial and convolutional neural networks. So these are used for, image recognition, soft like recommendation, natural language processing, these kinds of things. And like we mentioned earlier, they're composed of neurons and connections. You also weigh every input, or like sometimes the inputs have different weights at different neurons. Yes, so that's just trying to get, this is like the real artificial intelligence. This is the closest thing we have right now to real artificial intelligence. And then we have our feed forward neural networks. They have perceptrons, which is the most basic neural network with just like an input and like an output. And you also have your weights and your nodes, and they learn on the delta rule with gradient descent. And I think we go into gradient descent in a little bit later because something is based off gradient descent. I think
Yeah,
it's
I was gonna talk about that in
yeah.
backpropagation.
Yeah, the backpropagation stuff. Oh boy. Anyways, so this is a better picture of neural nets. So you have your input layer, which is all of the nodes or all the neurons that take input. Hidden layers, all the neurons that take, like process, and your output layer, of course, you have your output neurons. Okay. So last time we left off like in the middle of the convolutional neural network, which sorry for that. We just kind of sorry for that. So convolutional neural networks, they take your input image, right? And you assign weights to objects or aspects of it. Can differentiate between them. So like it can differentiate between things in the image, if that kind of makes sense. Like the different objects in it or aspects. Like if you have like blue sky, green grass, it can say, oh, this is a different color than this. So it can differentiate. Yeah. So pre-processing, you don't need to do much of it for convolutional neural networks. You do, however, need to pre-process a lot for your typical classification algorithm because classification is supervised. So like you can't, so if you're trying to just like train a model to, differentiate between a cat and a dog, then first you're gonna have to label a whole bunch of pictures cat and a whole bunch of other pictures dog. And then feed all of that in, right? You have to process the data before you feed it in. But really with convolutional neural network, it kind of figures it out by itself. So you're okay. So it's inspired by the organization of the visual cortex because, you know, everything in AI pretty much is modeled after the human intelligence, just, you know, trying to manufacture it, hence the name artificial intelligence, you know. Anyways, so convolutional neural network, we have these are our components or our layers of it. So you have your convolutional, pooling, flattening. The connected layers, sometimes I've heard them called fully connected layers too, but because in convolutional neural networks, typically they're fully connected. And that just means that every single neuron is connected to every single neuron in the next layer. So you also have your receptive field and your weights and biases that play into it. And then this is how you like go through the image. So you convolute it and pull it. Basically, both of them are making it smaller. So you go through, and if this were like, so we have a 3x3, we're doing 3x3 corresponding to a 1x1, if that makes sense. And you just go along your image, all that stuff, and convolute it, make it smaller, pull it, make it smaller, just make it easier. Break it into like little bite-sized pieces for your model to really, your network to, you know, really digest it, right? You have to do this a lot and a lot. But the other tricky part with convolutional neural networks is you have to make sure you don't do it too much that the image is like unrecognizable, and then the computer is like, well, now I don't know what this is, so I'm just not going to do anything. Anyways, so convolutional neural networks, we have this nice image here, and last time we went through, you know, convolution, and I think we briefly talked about ReLU, but meh, kind of. And we have pooling, more, do this over and over again until you get something that you can finally use, and then we flatten it. So finally, before we flatten it, the final thing after we're done condensing everything, doing all of the pooling and whatnot, that turns into a matrix. Flattening is basically just when you take your matrix and turn it into a column vector, right? So you know, like the 3x3 matrix turns into a 9x1 matrix, or column vector, really, because now it's a vector. Then that makes it really easy to feed into a neural network. So, well, I mean, it's already in the neural network, but that makes it easy to like start identifying things, right? So after that, we have our fully connected and our softmax thing, which Joaquin is going to talk about. Never mind. So
Okay.
yeah.
So as we just saw, you have the convolution step. How this works mathematically is basically you're taking some linearizing function. Usually this is in the form of matrix math. So this is like, you know, basic operators like you're going to be like multiplying and adding and subtracting. I mean, basically you're going to be using those kinds of things to minimize your data that you're getting from, you know, like how you saw in the last image. That's what you're doing in convolution. Okay. Now the problem with that is that while you're minimizing this data, whatever you're using to do that, if you're using a convolution step, this is linear. This is using a linear function. This doesn't account for nonlinear things like, you know, data that might be best assessed with like a hyperbolic tangent or, you know, sigmoid. You know, as you can see here at the bottom, like all of these functions we have here, these are things that are nonlinear functions. Usually, sometimes you might even have data that's like non-continuous or maybe like non-differentiable. You don't know. But anyways, what ReLU does is it rectifies the linear data. That's kind of how I'm looking at this name. So basically, anything in your data set that your linear, your convolution step can't account for, your ReLU is going to correct. So why is this something that's super useful? So like, let's say you have like a, I don't know, I guess like you could say like if you're analyzing like biological data or something, like what would be an example of this? I don't know. I had one on my head, but I mean like, you know, let's say like you're analyzing a data set and you have like negative data that your linear function can't account for properly. So you could use something like a ReLU to correct that negative data to be positive. So then you can like assess it and use it to like build on your model. I feel like there's a clearer way that I could put that, but essentially, I mean, like you can kind of look at this picture down here. Like what you're doing is as you can see right here, like it's getting rid of like negative noise. So like let's look at like the rectifier. For rectifier, you can see that the bottom on the left hand side for x less than 0, x less than 0, all of the negative data is just going to be 0. Okay, and then it assesses data that's x larger than 0. Okay, so then you're going to have those numbers and those probabilities. So why is this useful? Well, basically, you're convoluting and you're using ReLU on your data, and then at the end, you want to have you're going to have your data set once you flatten this data. Okay, so once you have your column vector, you might have specific things that you want out of that column vector, and you might not want negative values. That might be useless to you. So using something like a ReLU, you can basically just cut those things out with some simple math. You know, like how you can see right here, you have like a sigmoid function. I'm not sure if y'all know about that, but I mean, like all of these are just like basic mathematics that you can, I mean, pretty easily code. Logistic function, heavy side is basically like a 0 or a 1 based on like imagine like two lines. Basically, if your x is less than 0, then it's just 0, and if your x is greater than 0, then it's just 1. That's the heavy side function. So you would use things like that are nonlinear functions to basically like help assess your data. So you know, like you could get rid of noise. That's a pretty good way to think of this. So it helps the speed. They're pretty efficient at getting rid of stuff, and it simplifies your neural network because you don't have to like, if you run into a problem with data that can't be assessed linearly, you're not going to spend a crap ton of time and resources trying to assess that data linearly with your model. You know, you're not going to like have that kind of loop. You can get over things like that because I mean, like, I don't know. I guess one way that you can think of this is it's like is it like like you can have like an error with like a for loop where your loop just, you know, like continues to go on. I forgot the specific name. I'm too tired right now. But like if you don't have like an end to your for loop and your for loop just continuously goes on, you're going to get errors in your code. Kind of think of this like that. Okay, so that's why you have rectifying. You know, you have a rectifier for your convolution step. All right. So hidden layers. Hidden layers, we just kind of talked about these. These are the meat and potatoes. The meat and potatoes of your neural network. This is the important stuff. This is the brain. So you can see right here, right in the lower middle part of the page, you can see I posted like the neuron. You can see dendrites. Kind of think of dendrites. You know, you can even see right here, the dendrite is basically like that is like connections to like past nodes. I guess you could kind of think of it that way. Okay, then your central body is like what the node is doing. That's your cell body where you have like your nucleus. You know, that's all the thinking stuff. And then your axon is going to future ones. Okay, so how do neurons work? Basically, if you have a high enough activation potential, that neuron's going to fire and it's going to hit other neurons. Okay, and once you have a complex of these, you know, and you have, you know, thousands of neurons, millions of neurons, you know, billions of neurons firing, you can, you know, have a complex system arise and you have emergent properties. Okay, this works the same way with computers and artificial intelligence. Okay, so where does this happen in a neural network? It's in the hidden layers. You have like for any given neural network, you'll have your hidden layers, and each layer will have the same number of nodes, but these grow exponentially in complexity. So if you have 2 hidden layers, all of those nodes in those hidden layers can be connected together. Like Tiffany said, a fully connected neural network. So you can see right here, we have something like that. And in the middle part where you see that, let's say you have 3, okay, you can like scale that up so much. So you're going to have connections for 3 hidden layers, for all of the nodes in those hidden layers, for all 5 of those nodes in each layer, okay, and with the inputs and with the outputs. So, you can already see complexity is going to grow super quickly as you have more layers. And this usually makes your model more accurate, but it can overfit. So if you look at this equation at the bottom of the page, this is the optimal number of neurons before overfitting starts to occur, and this is the kind of like equation you want to follow. Yeah, I mean, it's pretty self-explanatory, I think. If you have any questions about that, then let me know. But yeah, you have a fully connected, and then you have all of your nodes inside of it. I mean, hidden layer is basically like it's the thinking part. It's the thinking part of the machine. And also another thing, I should touch on this. I kind of just skipped over it while talking about everything else. This is private stuff, so it's kind of like I guess you can kind of think about it like human thinking. Like we always question, like, how do humans think? Like what is like the really like the core of like consciousness, I guess, or like something like that. Like what actually makes all of these things tick. Well, for a neural network, it kind of works the same way with your hidden layer, because this is like private knowledge. It's like things that you can't really like, you can't know what, I mean, you can kind of narrow down on specific variables if you feed like information into a computer, but even then it's really hard to narrow down specific nodes inside of that neural network. So as complexity is growing, much less about what's going on inside of that neural network in those hidden layers. That's not Occam's razor, isn't it? What is that called again? That's like a chemistry thing. I can't remember what the name of it is. It's like if you can see something, then you can't know okay, anyways, I feel like that's just kind of a tangent. I thought that might help. But yeah, anyways. The more complex, the less you know what's happening in there, because there are more connections, and it's hard to know what value, what weight each of those connections or nodes is having on the output you're getting. But yeah, anyways,
Yeah,
hit me.
I think
Oh, is that
Occam's
good?
razor. I think Occam's razor is like the simplest one is the best or most correct or something.
No,
Like
Occam's razor is incorrect. I can't remember the name of it, but it's like, I remember Acre talked about it in chemistry, and it was like for a particle, like if you know like the speed of a particle, then it's harder to know where the particle's at. And I don't know. I'm talking with 9 p.m. Joaquin brain. Yeah, no, I can't
that
remember
sounds
it.
kind of familiar though. Like I feel like
It's like a quantum theory thing. Anyways, okay, let's go on.
yeah, we're just gonna
I'm getting tangent.
Yay,
Okay,
Softmax.
so Softmax. This is the thing that you saw at the end. So once you've gotten to the step where you flattened your data, okay, and you've simplified it as much as you want to, you've gone through your convolution and everything, your ReLU, you've done your pooling, so on and so forth. You repeated that however many times. Basically, you're gonna have all of your data, your final data that you want, optimized and ready in a column vector. But the caveat is that this data is not organized in any kind of way. It's just there. So the good thing is that even though this data is unorganized and maybe you can't see anything out of it now, you can organize this data and get a lot of information out of it. Okay, so essentially what we can do is, as we already know, you have you've summed the values of the data from whatever you're analyzing that can be made numerical. And what you want to do is you want to classify this. Okay, so what you're doing in this step, I basically, you're trying to make this vector be from greatest to least, so you can predict. So you can give a prediction out from this neural network, on what it's actually looking at. So this is what Softmax does. It basically takes the values that you've gotten and it interprets them into probabilities. The way it does this is that it's basically going to use, I'm pretty sure this is just like basic probability models and stuff like that. And it's going to use those to create like probabilities, percentages that you can rank in that column, as opposed to just having those values. Okay, so what you can see right here, I basically describe it. Your probability is on the left-hand side. You can see down here at the very bottom of the page. I can't remember what that Greek letter is called. I think that's, I want to say sigma, but I know that's wrong. Is that wrong? I don't know. Anyways, and that's defined for z, which is your value, the value in that column vector, and the column vector is I. So you're at the ith column vector with value z, and you're finding the probability. On the right-hand side, you can see, just as I described, you have an exponential, and it's risen to that value at the ith column, and then that's divided by the sum of all the values prior to. Or no, never mind. I'm sorry. That's incorrect. It's the sum of all the values in general. Okay, so you're taking all of the values in that column vector, and then you're dividing that value over them. This will give you a fraction, and you can use that to basically get a probability. That's what this function is going to give you. Or it's going to give you a fraction, and then that is like a percent. Once you have that percent, basically what you can do, you can just use basic algorithms. You're going to take that column vector, organize it out, and then you can have like your greatest probability. Actually, I think this is on the next slide, Tiffany. I might have code. Yeah, so you can see right here, it's a lot simpler, when you look at it like this. NumPy kind of handles everything super easily. So you can see you have that exponential function in the return statement in your array right here. So you can see your data right here, -1035. It's going to take that data, and it's throwing in that data into Softmax. Yeah, and then from your print statement, you can see right here your return values. Like, as you can see on the right-hand side of this after the hashtag, these are the probabilities you're going to get. Okay, so this is how likely it is for you to have a cat, or that's how likely it is for you to have a dog, so if it's 0.002, times that by 100, likely to be a dog, is your model going to think it's a dog? No, it's going to probably think it's a cat. So this is how it predicts things. You're going to receive cat, 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 dog. You can see on the very far right, this one's the highest. So it's going to probably think it's a dog. 87% chance it's a dog. That's a pretty good guess. And really, in your model, you could probably define where you want that to be. So, is 50% likely going to be a dog? Is lower than 50% going to be a cat? Those are things that you could add into your own model. Okay, so backpropagation. This is, okay, so last week I kind of messed up on this. We were talking about feed forward. Feed forward is basically a neural net where you're just moving forward, okay? You don't have any kind of backtracking, and you're only moving through your nodes. This is kind of inefficient because you can kind of think about it like this. Say you're walking down a mountain, right? You're walking down a mountain, and you're trying to get to the bottom of this mountain. And you see a rock right in front of you, okay? Now, you can't steer to the right and you can't steer to the left to get away from this rock. But if you walk backwards a bit, and then you go left, and then you keep walking forward, you can get clear of the rock and keep going down as opposed to going back up. This is kind of how gradient descent works. That's actually, I mean, really the best way I can explain the math for this. It takes vector calculus, and you would have to do partial derivatives and calculate a gradient for this, but sounds super complex and like, you know, bad, but it's not actually. It's a pretty simple thing. I mean, this is basically just like taking a derivative of a function and then trying to find a minimum value. Your minimum value will get you to the bottom. How do you find minimum values with derivatives? You're going to find the zero, or you're going to find the derivative equal to zero and then solve for those things. Backpropagation basically works on that kind of principle. You can think of it like that. You're really just trying to get down a mountain. That's what your model is trying to do, and you're working that out into math. Kind of sounds bad, but I mean, like if you look at this on the right, that's kind of like that's like a super good way to kind of think about it. So like your best initial guess is like just going straight down. Your worst initial guess is like you're just going all over the place. Actually, I'm not sure if I really agree with that. I'd say your worst initial guess is probably the one where you're going all the way out to this angle. So you see the one that follows the dotted line. That's probably your worst guess. Well, actually, maybe I'm contradicting myself. Hold on. I mean, I guess, yeah. Let's put it like that. Or no, because we're gonna go with backpropagation. Okay, so let's say that the one with the dotted line, that's you're like, okay, best initial guess is like going straight forward. Worst initial guess is like you go down and then you have to change your position, but you're continuing to go down the whole time, right? This is like a feed forward. The straight line, the solid line, that's like bad. That's like your feed forward. You can avoid these things if you have a gradient. Oh wait, no. Okay, I'm completely screwing this up. I'm so sorry. Okay, following your gradient is basically following your way going down. So your gradient is like you want to either stay at zero or you want to stay like, let's say like a negative derivative, okay? You want to keep going down, okay? So I'm sorry. Your worst initial guess would be your dotted line, all right? Because you're still trying to go down, but you're not following the gradient, okay? So you're still trying to get to this final point you can see, like that they all end up at. But the thing is that because you're not following the gradient, this really isn't going to be your best guess. And it's not going to get you there as fast as a guess that would take that gradient into account, okay? Following the gradient is basically like saying, in your future, I mean, like, kind of think about this like, let's say you have a y function, and your y function is, it's increasing, so you're going from 1, 2, 3, 4, okay? Or no, actually, I'll use something a little more drastic. Let's say you're going 1, 9, 13, 15, okay? So you're still increasing that value, but what do you notice about that? Its slope is decreasing, okay? As opposed to something that's going like 1, 2, 3, 5, 6, or 1, 2, 3, 5, 9, 28, 56, 142. You want to go down that path. So that's what gradient descent does. It finds you the best slope. There you go. That's a clear way to do it. I'm sorry I messed that up for y'all. But yeah, I mean, you're basically working in vector functions. I just want to get the idea across to you so you understand that, because basically what your computer is doing whenever it does this is it just means that it's going to move back. It's going to move back through your nodes and then go back forward so it can find the best path to get like the most probable guess. Okay, that's what
Yeah.
you want to do.
Mhm. If you're really curious about this concept, What's that guy's name again? He's really famous for like pioneering in AI. I think it's Andrew Ng, like NG.
Yeah,
I don't know if I'm saying his last name right, but my guess is Ng. But anyways, so there's a free online course. It's called like Intro to Machine Learning or something, actually. I don't know. But like the very first lesson is like something right about this. So yeah, he basically just describes it like how Joaquin described it, you know. If you're trying to get to like the lowest point, but like sometimes you see on this one it's like a net, right? And there's one lowest point, but sometimes in your data you have like there's not there can be local minimums and absolute minimums. So if you keep going down and down and down, you're like, oh, this is the end. But no, it's not really the end because you're trapped yourself into like a hole that's not the lowest one, right? So you have
exactly.
kind of like an answer, but not the best answer. So with backpropagation, you kind of go back and you're like, okay, let me just make sure this is the deepest hole and try something else. You know what I mean?
Yeah, that's the best way to put it.
Okay. Yeah, backpropagation, it's kind of like most of the advanced neural networks use backpropagation. I mean, yeah, it's a pretty good concept.
It saves you a crap ton of time because I mean, like
Yeah.
how you
Mhm.
just said, if you get stuck in like a local minimum, but it's not your absolute minimum. It's not the most efficient your graph could be. I mean, not graph, your neural net could be. It can be pretty difficult to get out of that.
Mhm.
You can avoid those things if your model takes that into account and it has some
Yeah.
way to like measure its surroundings and know like, is this the best, like is this the lowest, I guess this is one way I could put this, is this the lowest energy I could be at? Can I be more efficient? But
Mhm.
anyways, let's move on. I don't want to
Yeah.
confuse anymore.
Yeah, if you have questions, feel free to ask. Oh, yeah. So this is just convolutional neural networks. There's a lot of different like types or different ways you can like layer it, right? So I just put together some of the more common ones. Actually, Lynette, I don't think it's really common anymore because that was like 1990s or something. That's like the very first convolutional neural network, and that's when they started doing like convoluting stuff, layer like pooling. That's when it first started. So it's called Lynette or Lynette 5 because there's 5 layers. So yeah, most of the CNNs are like kind based off of Lynette. It was like the very first, it was a big thing during that time. But nothing really happened with convolutional neural networks until like 2000s. So like somebody developed Lynette in like 1990 something, and then they were like they just used that for a really long time, and then they were like this is fine, and then somebody like way later, I don't know why they didn't think of like improving this, but oh well, whatever. So yeah, Lynette. I have a picture. I have pictures on the next slide, so we'll see that in a second. But yeah, um, so AlexNet is a different way of arranging your convolutional neural network. It's the guy who made it is named Alex, so surprise. But it was first to introduce ReLU. Before that, the convolutional neural networks were using. It's like the I think it's like the function is like something H. It starts with a T. Like I'm tempted to say it's like trip H or something. But anyways, before that they were using a different type of like so instead of using ReLU to like, stabilize things, they were just like, nope, we're just gonna use this other type of function that it's a lot more inefficient. So this was the first to introduce ReLU, and everyone was like, wow, that's amazing. That, makes it really a lot more accurate. So yeah, this one has 8 layers, 5 convolutional and 3 fully connected, and yeah, has is also the first to introduce the overlapping pooling. So you know how in the other pooling, like whenever we pool stuff, we just split it up like into little bite-sized chunks, right? And then each of those chunks corresponds to like one little square thing, right? But with overlapping pooling, you overlap it. So like if we had like a 9 by 9, and we were doing blocks of 3, so like a 3 by 3 and a 3 by 3 and a 3 by 3. So instead of splitting that 9 by 9 into 3 chunks of 3 by 3s, you could maybe do like 5 of them and like overlap the way you're splitting it up. Does that make sense? Yeah. So they did overlapping pooling, which also, you know, made it more accurate too. So okay, next one is GoogleNet, or it's so when I was reading about this, the Lynette, like they capitalized the O because as a reference to Lynette, and then somebody was like, wait, like in the comments or something, they were like, is it like pronounced Goog Lynette or Google Net? And I was like, well, Google Net just sounds stupid, so I'm hoping it's Google Net. Anyways, this is also called Inception version 1. And of course, there's versions 2 and 3 afterwards when they improved it even more, but I think Inception is a cooler name. Anyways, so this image on the left, or sorry, on the left, right. My brain is fried. The image on the right is the Google Net. It's got 22 layers, and it's just, yeah, I know the picture is kind of hard to see, but I just kind of put it there so you could have like a idea of how they like just how complex it is because it has a lot of layers. 22, which is like way more than the previous ones, 5 and 8, way more. So yeah, this one, Google Net, is really like it's a convolutional neural network, of course, but you know how like you can train something to like, I don't know, differentiate between cat and dog, or like uh zebra and like a horse or something, I don't know. But with this one, it's trained to identify images into 1 out of 1,000 possibilities. So it has like it's like got a little bit of like sorry, it's got a tiny little database, not tiny, it's 1,000, but it's got a little database, and it's already like this is an already built model, and it's not like a architecture, it's not so these architectures, like you could train a Lynette model to do something, or you can train a Alexin to do something. This is an example. So like this is a neural net that's out there for like use. So I mean, if you wanted to, I guess you could model another one off of it with like, I don't know, different items or something. But yeah, so about 1,000 like common household items, and you feed it a picture and it determines whether it's one of those items. I think actually if you feed it something that's not one of those items, it'll just give you whatever's closest. So, not bad. Okay, so the last one is ResNet, and it's not my ResNet. Oh, wait. Oh no. Andrew, I don't think you'd get that joke. You didn't actually go to TAMS. But yeah, the weird Wi-Fi thing is my ResNet. So, and it's also like really sketchy sometimes. For the most part, it worked okay, but like, yeah, no. Anyways, so this is a residual network, ResNet, residual network, and I actually did not elaborate on this. Wow, how nice of me to do this to myself. Okay, okay. So residual network, it's just like, so to my understanding, because I need to make sure that I don't tell you something wrong. So, okay, so like in traditional neural networks, the layers like feed into the next layer. So, like it just goes from layer to layer to layer, all the way down. But with the residual neural networks, they have residual blocks in them. So of course, they still feed into the next layer, but each layer feeds into the next layer, and it also feeds into the layer that's about 2 or 3 like layers away. So okay, I'm gonna use this as an example and say, look at this like green chunk in the middle. So this one feeds to all these blue ones, right? But if this were a residual neural network, it would also feed to like the next green chunk, or maybe like the next like row of 4. So they hop around. And that's pretty much just how they're different. Yep. So you feed it, of course, everything is continuously feeding forward, but you're also jumping. So like like leapfrogging over your layer. So you're feeding it to the next one, but you're also feeding it to like the 1, 2, or maybe 3 like layers away, you know? Okay. Yeah, there's some sort of math concept behind that to why it makes it more accurate, but this is beginner AIS, so I'm not gonna go. If you really are interested, we can go over that though. But yeah, the math stuff is more of Joaquin's strong suit, so okay. Yeah, anyways. So, oh yeah, pictures. So this is Lynette 5, you have your input, and you have your, condensing, convoluting, what have you, making it smaller, 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 smaller again, and then flattening into like a vector and then feeding that in. Then you have your output. So AlexNet is a little bit, the image is kind of janky, but it's a lot harder to read. But so you notice you have your input not vector, you have your input layer, you have your inputs, you put them in there, of course you pull them, make them smaller, 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 smaller. And whenever time you pull, they're all connected, interconnected to each other. So you have all this stuff. And then you get it into your nice little block thing at the end, feed that into. So yeah. Oh yeah. So okay, random forest. We forgot to talk about this when we were talking about machine learning. Random forests it's not a neural net. It's just I think it's just like a type of machine learning, like a machine learning model or something. Correct me if I'm wrong, Joaquin. But yeah. So we shoved it onto the end of this GA because we were like, oh no, we didn't talk about it because it'd be a shame to not talk about random forest. It's so useful. So really, it averages predictions of decision trees. So several trees make a forest. Haha. Okay, but you either do it by. I'm sorry, I'm like dead right now. No. Anyways, so you either decide it by majority voting or averaging. And what I mean by that, okay, so look at the picture to the right. So you have a random forest. All of these are decision trees, right? So you have your input or your data, shove it into all of those trees. So each one of those decision trees will calculate an output, right? And so let's say you have a picture of my cat, and then you feed it to like tree 1, tree 2, and tree 3, tree 4, 5, all the way to tree n. So let's say trees 1, 2, 3 say that it's a gray cat, and then tree 4 says it's a gray dog. So the majority voting is 3-1 gray cat. So your final class that you're getting is going to be your gray cat. And this works not just with classification, but also regression. It's very versatile actually. So and the concept is simple. You're just trained because all the decision trees are like little models, right? So it's like you're running a bunch of models on something and then just taking like the average result you get, which is gonna be pretty accurate, or fairly accurate at least, depending on you might have screwed something up in your trees, but yeah. So so let's say we're predicting like rainfall or something, and then we give it the data like for a year or something in Texas, but kind of dry, so Texas. So like tree 1 says, oh, I think it'll rain. I have no idea what like actual rainfall levels are in Texas. So like he'll be like, okay, tree 1 will say, I think it'll rain 5 inches during like, okay, let's look at rainfall during June. And then tree 1 says, okay, maybe it'll rain like 10 inches of rain during June. And tree 2 says, no, no, no. I think it'll rain 12 inches during June. And tree 3 is like, I think you guys are both wrong. I think it'll rain 11 inches during June, right? And with random forest, you have all these trees. You add them up and you take the average. So 10, 12, 11, that's 33, 11 is your average, right? So your final decision, your random forest is going to say, okay, Tiffany, look, in June of Texas, it's going to rain 11 inches. That's what we all came together and decided, right? So you all have your trees, and they'll give you their best guess. They're like, oh, I think it's gonna be 9 inches, or I don't know, whatever, and then you average it, and that's your final answer. It's pretty intuitive. So random forest is really easy to train because really you're training a bunch of like tiny models. Okay, this is a better way to explain it. So let's say I am going to TAMS for the first time. So I'd ask a senior, I'd say, hey Joaquin, how was your TAMS experience? And he would tell me, like, I don't know, this was good, or this class was nice, or I like this professor, or don't forget to do this. And I'd be like, okay. And then I'd go ask my other friend, or Bonnie. I'd say, Bonnie, how was your TAMS life? And she'd give me information too, but like differently. So each of these trees are like asking the same person, asking different people the same question. And then you're taking the average of all those answers, and that's your, final answer, right? So that's your like overview of TAM's life, because each one of them might tell you something different. Like, I don't know, somebody might talk about the food at TAMS, and somebody might talk about, academics at TAMS, or the student life at TAMS, or the clubs. So each of these trees will look at different features of it and then take their best guess based on that feature, if that makes sense. Because you don't, all of your trees are different. Of course, in a forest, no two trees are the same. So same deal with the random forest. You just have a lot of different decision trees. They're looking at different aspects of your input data, and then they spit out their answer. They're like, okay, I think this is nice. Or maybe somebody else would say, no, I hate it, TAMS. TAMS bad. And then that would be like another prediction. You average that in with whatever else. So yeah, and there's also the good thing about this is there's no danger of overfitting if you have enough trees. I mean, if you have like two trees, you're overfitting to like those two people. So, or if you only had one tree in your forest, which is that even a forest anymore? But if you had one tree and you asked only one person about TAMS, you would overfit your TAMS experience to that person's experience, if that makes sense. If you have enough trees, then you're cool. Whatever. You have a good like general overview because you have a lot of trees. So, it's really good because it random forest rarely over or under fits. It normally gives you a very accurate result. Okay. And it also works well without having to tune. So like, I don't need to, tune Joaquin and Bonnie and Shreya and be like, oh, like only in these parameters, you can only talk about these parameters of TAMS. So yeah. And also, okay, decision trees, oh, did we actually go through decision trees like in our analogy?
Yeah, I think so.
We definitely mentioned it. I don't know if we went in depth though. But decision trees, obviously, it's just like these little things, right? So you take your input stuff, and then the input says like, okay, so like it splits it by feature. So if it says, okay, I give it like my picture of my cat, and it says, okay, is this like a light colored cat or a dark colored cat? And if it was light, it's split here, dark split here. And then like dark, it would be like, is it dark gray, or is it like, Russian blue, or is it black, or like something like that? And then it would split and split and split and split and split. And then finally it would say, oh, this is a light gray cat with stripes, with like black accents and white paws or something. And then that would be your like, and it would be like, oh, this is Tiffany's cat. So what's that called? They make you do it in like dichotomous key. It's it's basically like a tiny dichotomous key. And yeah, so okay. Each node is, well, obviously a node, but the nodes at the end that don't connect to anything else are leaves. Because your trees, leaves, decision trees, random forest. Yay, okay. Yeah, random forest is pretty intuitive. It's simple, it's easy to get, and it's really accurate, like almost all the time.
Okay. Alrighty.
Oh, that's it. Thank you so much for coming.
I remember Heisenberg uncertainty principle. Yes, that is the particle thing. Okay.
Yeah, of course. Thanks for joining us, Andrew. Sorry, I think we're both kind of dead right now, but yeah.
Our brains are fried.
Let us know.
Mine is. I hope some of this was clear.
Yeah. Neural nets.
Dang, we really need to get on posting this stuff because I feel like nobody's gonna see any of these GAs unless we put them online.
Yeah, Henry. Oh my God, Henry always sends like the link to the cloud computing thing, and I look at it and I'm like, cool, I'll post it. And then I don't post it. So, Joaquin, didn't you say they like expire or something?
Yeah, I thought they did, but Henry said they don't.
They don't. Okay. Well,
I don't know.
I guess I'll just make a master post or something and be like, these are all of our lecture recordings so far.
I'm not sure if y'all are comfortable with doing in on like a what is it? Oh, what am I trying to think of? Like a public channel, but I'd like to at least do like an unlisted YouTube channel for all of these.
Yeah. Like get it out there or something.